Today we're covering material from section 4.1 on polynomial functions and modeling. Here are all our objectives. Today we're talking about polynomial functions. In general, a polynomial function p is given here, where a sub n is going to be a number, we have x to some power n, and we write them in descending order. So we do this all the time. So things like x cubed plus 2x squared plus 9x minus 50, right? We always write the exponents in descending order, and here we have nothing, down to our term without x in it entirely. So we're talking about, in general, how can we deal with these functions? They have a lot in common. In general, when talking about these functions, we want to be able to identify the leading term, which is the biggest exponent overall. So in this example above, x cubed would have been the largest example. You have to be careful though, because we could have something like x cubed minus 4x to the 5 plus 9x minus 200. And our leading term is hidden here just because it wasn't written in the proper standard order. Our leading term is always the term with the largest exponent. So here that's negative 4x to the 5. Our leading coefficient is the number that's right in front of that largest exponent. So in this example, that's negative 4. And then the degree is, of course, that exponent that sits in that leading term, the degree n. When we have something where n is 1, we call it linear. When something we have where n is 2, we call it quadratic. When n is 3, we call it a cubic. And when n is 4, we call it a quartic. If we have an n higher than 4, we don't really give it a name. We just call it a polynomial of degree 5 or higher. I only use the special names for these 4 special cases. You don't have to use these names, just get used to hearing them. So you could be given something like this quadratic function where we have f of x equals x squared minus 2x minus 3. And we want to be able to pick up all of these different concepts off of our quadratic function. This is more of a review of what we did in our chapter 3, but we're going to see how this expands now to higher degree polynomials. So this function actually does factor. We're going to factor it into our 2 binomials that have the leading x. Now we want to think about things that multiply to 3 and add to 2. So let's try 3 and 1, because we know they have opposite signs since we end in a minus 3. So it goes minus and plus. Now to find our actual zeros here, we take those factors and we set each one equal to 0. So x minus 3 equals 0 and x plus 1 equals 0. Here we get x equals 3 when we add the 3 to the other side. And here we get x equals minus 1 when we subtract 1 to the other side. So these are our zeros, x equals 3 and minus 1. Now our x-intercepts are, of course, the points 3, 0 and negative 1, 0. To find the y-intercept, of course, we want to plug in x equals 0, and we get 0, negative 3. Then we look and say, oh, my function does have a minimum. And to find its minimum, we look at its vertex, 1, negative 4. So the minimum is negative 4 at x equals 1. There is no maximum because it's a quadratic. Our domain is everything on the x-axis that we can plug in, which of course here is negative infinity to positive infinity. And our range then are all the y values that are hit by this function. That's negative 4 up to positive infinity. Hint, hint, the domain here is for any polynomial is always negative infinity to positive infinity. That is always true. So you can always keep that in mind. Now let's look at a cubic. Let's say we have something like this, where we have g of x equals x cubed plus 2x squared minus 11x minus 12. You can have the factored form there. So to find its zeros, of course, we want to set x plus 4 equal to 0, x plus 1 equal to 0, and x minus 3 equal to 0. Then we get x. Let me go ahead and just list these out. X equals negative 4 for the first, x equals negative 1 for the second, and x equals 3 for the third. And yes, it is always the opposite of the term that sits here, because you always have to add something like the minus 3, which add to the other side and becomes positive. So if that's a pattern you've picked up, that's always true. Our x-intercepts then are the points, negative 4, 0, negative 1, 0, and 3, 0. For our y-intercept, we want to plug in x equals 0, and we get 0, negative 12. For a relative minimum, we want to look at the graph here. We see we have a minimum at this point. It's just relative because, of course, we can't pick a specific minimum from this arrow over here. So we just are looking at where we have this valley. So our relative minimum is negative 20.7, and it's at 1.4. And we will be using the graph here for these types of examples to get used to picking up the min and max. And we're going to show you as well how to do that in this lecture off of the calculator itself. Moving on to maximum, though, you see we have a maximum at this hill. The max is 12.6, and it's at x equals negative 2.7. Oh, great, 7. Now, our domain is, again, negative infinity to positive infinity, as are all polynomials. And our range here is also negative infinity to positive infinity. You can see every y value would have been hit by this function at some point, given the arrows going up and down. So that is it kind of for those standard polynomials that you'll see. You do have some of these on your homework. Some other kind of pictures just to give you an idea. Anything, of course, that is written in powers of x's. So our quadratics like we have here, our constant functions, because this is really an x to the 0 power. Those are also considered polynomials. And then, of course, we have our cubic and we have our quartic. Things that are not polynomials are things like our absolute value function, our square root function, any kind of fractional exponent function, and any kind of fractional function in general. These are all non-polynomial functions. These are not what we'll be covering this chapter. So in general, a polynomial function is what we call continuous. So that means that it has no holes or breaks. I can trace the entire function with my pencil, and I do not have to pick it up once. It's also what we call smooth. It doesn't have any sharp corners like in the absolute value bar function. So that is kind of what you want to look for. A straight line, as in a horizontal line, is also considered smooth. Furthermore, as I already said, the domain of all polynomials is the set of all real numbers, so that's negative infinity to positive infinity. Now, we're going to talk about the leading term test. You see, with any polynomial, the leading term determines the shape of the overall polynomial. So as you get to the edges of your graph, as x gets really big or really small, each polynomial is going to behave in one of 4 ways. Either both ends are going to go up, both ends are going to go down, one end goes down and then the other goes up, and one end goes up and the other goes down. And all of this can be determined based off of if n is even or odd, and if your leading coefficient is positive or negative. Now we leave these little squiggly lines in here to represent, we could have a few different kind of lumps and bumps in here, but we don't know how smooth the curve is in the middle, but we know the overall trend goes a certain way. So for example, we don't know how level it is in the middle kind of section here on a graph. We just leave it vague and call it this general overall shape. But that's what we wanted to identify with the leading term test. So let's do that. Here's some examples We're going to talk about what the leading term is in each of these and then match them to the graphs on the next page. So here, for the first example, my leading term is 3x to the fourth. That means a sub n is 3, and my n is 4. So a sub n is always the number in front, n is always the number in the exponent. Well, a sub n being 3 is positive, and n equal 4 is even. We're going to take each of these notes on these, and then we'll see what happens in the next page. So in the next example, number 2, of course, a sub n is negative 5, and n is 3, which means we have a negative and an odd. Here, in example 3, a sub n is 1, because there's nothing written here, which is positive. And here, n is 5, which is odd. Okay, lastly, a sub n is negative 1. Again, the number's not written here, but anytime it's missing, we call it a 1. This is negative. And our n here is 6, which is, of course, even. So looking at what happens then in the next page, I have those same notes written in here. Example 1 being even and positive. Even means we're going to go up on both sides, or we're going to go down on both sides. Positive means, of course, that we're going to go up. So I erase the bottom part here, and I know I'm going up and up on both sides. So that's actually D. Done. I can cross that out for the rest of them. Now looking at number 2, I have odd and negative. Odd tells me that it's either going to go down like this, or it's going to go up like this. But of course the negative makes us think we got to go down overall. We can't go up overall. So we're looking for this overall shape, or of course B. Notice how it goes up or kind of down as we go down this way. That's exactly what's happening here. And then we keep going down as we described here. So that's B. Now we look at odd and positive. So we know that they need to go opposites. Essentially, I can't have an up, up, or a down, down. It needs to be a down and then an up. And of course, positive means I'm kind of trending upwards overall. That, of course, is A. Now for the last one, I'm even and I'm negative. The even tells me that I need to match. So I know I'm going either up, up like this. Let me draw a little better. Up, oh my goodness. Up, up like this, or down, down like this. And of course we're negative, so we know we're going down. Just like this. And the down, down comes from part C. So it goes D, B, A, C. And again, you're just looking at the overall trend. We know even means they are symmetrical, essentially, it matches. And I don't know what happens in the middle with this weirdness, but I do know that they both point downwards, kind of giving me C. So that's the general idea. The leading term determines the overall trend for the function. And that's exactly what we picked up here with this matching. Now, whenever we want to find zeros of a polynomial, we know that we need to take each of those terms and set them equal to 0. That's how we solve to find our C values where f of C equals 0. And then, of course, as we've seen before, that translates into a point that represents an x-intercept on the graph, C, 0. So when we look at something like this as find the zeros of f of x, we know we can either look at the graph and say, oh, this is where we cross the x-axis, or we can just solve it algebraically. So notice how I have x minus 2 several times. Well, let's set that guy equal to 0 and solve. We get the same answer either way, so we're just going to solve it once. And then we have an x plus 1 to set equal to 0. So here I get x equals 2, and over on the right I get x equals minus 1. And I didn't need to set all 3 of these equal to 0. Of course, it would have gotten x equals 2 3 times. But that copy of x minus 2 happening 3 times does play a role in the graph, and we're going to see that in a moment. But for now, my zeros translate to these x-intercepts as well. -1, 0, and 2, 0. Now, if I'm given something like this, where I can't factor it, well, that would be quite challenging to factor. It might not be impossible, but quite challenging. We can still determine if 3 is a zero of the function, because we can plug in and find f of 3 and say, does this give us 0? 0, question mark. Well, I don't know. Let's find f of 3. That's 3 to the 4th minus 7 times 3 cubed plus 7 times 3 squared minus 4 times 3 plus 57. Now I'm going to throw this in my calculator to see what we have. Let's see. I have 3 raised to the 4 minus 7 times 3 cubed plus 7 times 3 squared minus 4 times 3 plus 57. And unless I did this incorrectly, let me double check. 1, 2, 3, 4, 7 times 1, 2. Yep, let me check one more time in my calculator. And 3 times 3 times 3 times 3. I'm using my phone here, so it's not the greatest. 3, 9 minus 4 times 3 plus 57. I had thought so. We do, in fact, get a 0 here. So, I highly suggest having a real calculator in front of you. Doing these phone calculators are a pain. However, when we plug all this in, we do actually get 0. So that tells us that 3x equals 3 is a 0 of f of x. So the point 3, 0 is an x-intercept. And we didn't have to factor here, thank goodness, but we can just plug it in and find out what you get. Now, talking about that case where we saw those repeated 2's, when we have that, we're going to end up with something like x minus c to the k, essentially that repeated factor, appearing whenever we fully factor the polynomial. That means that x equals c is a 0 of the polynomial. And if k is odd, then we're actually going to see the graph cross the x-axis at c, 0. And if k is even, then the graph is just going to be tangent to the x-axis. So we're going to have something more like this. That sits just touching the axis, not fully crossing it. That number k that we have in that exponent is called the multiplicity of x equals c. So the multiplicity of our 0. And that multiplicity is what we're going to use to determine, are we crossing the graph, so like that at a certain point, or are we just tangent to the graph like that one? So here's an example. Find the zeros of the polynomial and state the multiplicity of each. So we have 1, 2, 3 different terms with x's in them. We're going to set each one equal to 0 and solve. You can ignore the exponent on this part. So I have x minus 5 equals 0, x plus 3 equals 0, and x equals 0. So just grab the part inside the exponent. The exponent itself doesn't make a difference because 0 to the 4 is still 0. So we focus in. We look at x minus 5 and we add 5 to both sides. I get x equals 5. Then I have x plus 3 equals 0. I subtract 3 from both sides, and I have x equals minus 3. And then with the last one, I just have x equals 0. So for the first one, x equals 5, that is raised to the 4th. So that has multiplicity 4. Similarly, x plus 3 gave us the x minus 3 term. That has exponent 3. So that has multiplicity 3. And the last one at x equals 0, that came from our x squared term, that has multiplicity 2. So we know this one will be tangent to the graph. We know this one will cross the axis. Oops. And we know this one will again be tangent to the graph when we actually look at it. All right, next example. Again, we want to find the zeros and the multiplicity of each. And for this one, we have to factor it ourselves. So this is digging back into the factoring by grouping that we practice in the Math 24 worksheet. What we want to do first is factor out an x squared from the first two terms. Then I'm left with an x from the first term and a minus 2 from the second term. Then what we're going to do is factor out the 9, whatever is in front of the next term in front of that x. I factor out a minus 9 and I'm left with x. And then if I factor out a minus 9 from the plus 18, I'm doing the plus 18 divided by minus 9. That gives me a minus 2. Notice how this minus 2 term repeats. That's exactly what we wanted here. So now we have x minus 2 factored out, and I'm left with an x squared and a minus 9 term here. Well, that x squared minus 9 can be factored again into x plus 3 and x minus 3. If any of that is a little bit vague to you, please go back and watch the worksheet 4.1 examples video. We go through this in a little bit more detail, a little bit slower. But here we're using our factoring by grouping from our cubics example, and then also our square minus a square technique here. But here we are with our 3 factors that make up our x cubed polynomial. And if we set each one equal to 0, we have x minus 3 equals 0. On the first one, x minus 2 equals 0. I add 2 to both sides, x equals 2. If I then have x plus 3 equals 0, subtract 3 from both sides, I get x equals minus 3, and I get x equals 3. And each of these have multiplicity 1 for all 3 of them, because they all have a 1 in their exponents. But we had to factor it first to be sure. Now we're going to look at the only kind of quartic function I'm going to give you in this course. And that's because we actually do have a technique for factoring this. See, what we're going to do is set u equal to x squared, and we're going to factor it like that. So now our new function is going to be u squared plus 4u minus 45. If I factor this, I'm looking at u and u, and I think about things that add to 45. I have a 5 and a 9, and they add to 4. So a 5 and a 9, and of course I have opposite signs since they multiply to a negative, and I need to put the plus with the 9. So now I have, instead of u's, if I put back the x squared term, I have x squared plus 9 and x squared minus 5. Now my x squared plus 9, that's actually never 0. So I actually never get, well, you'll see what happens. If I try to put x squared plus 9 equals 0, then I get x squared equals negative 9, which of course can't happen. So that's actually going to contribute no zeros. We actually just don't have to look at it anymore. We're going to carry it along. And essentially we're going to look at the x minus 5. And this is going to factor in x plus root 5, x minus root 5. Again, using that square minus a square trick that we've talked about before. So then my zeros are x equals negative root 5 and x equals positive root 5. With multiplicity 1. on each. Again, a 1 in the exponent. Again, just note, x squared plus 9 just contributed nothing. We fully factored x squared minus 5 into x plus root 5 and x minus root 5, and each of those have multiplicity 1. All right, moving on to look at how our calculator can really help us here. So if we want to look at finding the zeros of this function, 0.1x cubed minus 0.6x squared minus 0.1x plus 2, I certainly wouldn't want to have to factor that if I can avoid it. So let's look at its graph, use the graphing calculator to look at the graph, and hopefully see the zeros, the 3 zeros that we have listed there. So let me get our calculator pulled up. There we go. And you can see I've plugged in that function for my y equals. If you want to follow along with your calculator, this is what I set the window to. And then we look at the graph, and it's looking pretty good. We want to figure out where our zeros are. So what we're going to do is second calculate. We're going to go down to 0, and I hit enter. Now you see where I'm sitting on the graph. If I hit to the left a little bit, and I'm now to the left of the first place where I crossed the axis, that's where I'm going to mark my left bound. Now it asks for my right bound, so I'm going to go to the right of where I crossed the axis, and I hit enter. I hit enter one more time, and there I'm given my first zero, negative 1.680. Now we can do this again to get our second place where we cross the axis. I hit second and hit trace to pull up calculate. I go back down to 2 for 0. Now I'm going to pick my left bound to be just to the left of the second place where I cross the axis. I hit enter. I scroll to the right of the second place where I cross the axis. I hit enter again. Now you can see the kind of window that we're zooming in on to calculator 0. I hit enter one more time. And again, I get my 0 calculated for me. It is 2.154. So we can do this process a third time and focus in on our third 0. We'll do that now. Hit clear to remove where we were. I hit second, trace to pull up the calculate, and I hit enter on 0. Now I'm going to scroll to the right until I'm just to the left of where I crossed the axis for the last time. I hit enter. I scroll to the right of where I crossed the axis the last time. I hit enter. I hit enter one more time, and there you have it, our third 0, 5.526. So that can help you a lot for these vague graphs in exactly finding out where your zeros are. Now going back to the slideshow. You can see those are exactly the zeros that we picked up when, let me turn my pen back on. There we are. When we went back to the calculator, these are exactly the 3 zeros that we picked up. Now on to our next example. So here we have this m of t function with these awful decimals in it, but it's used to estimate the number of milligrams of a pain relief medication of ibuprofen in the bloodstream T after 400 milligrams, in the bloodstream T hours after 400 milligrams of the medication has been taken. Find the number of milligrams in the bloodstream at T equals 0, 0.5, 1, 1.5, and so on and so forth up to 6 hours. Find the domain, the relative max, where it occurs, and the range. I have this broken out into a few components for us here. So let's jump to our calculator to do part A to find the values for 0, 0.5, and so on and so forth, because I would really like to avoid having to plug in, 12 different numbers into this function if we can avoid it. So let's see how that looks. Going back to our calculator, and if I go to this next window I have open, there we are. I've plugged in my y equals here. It's certainly taken its time. There you have it. Plugged in the function just like it gave before. And now I can go to my graph. and you'll see exactly how this function looks. To get it to fit on the window like this, you can see how I set my window to go from, on my x-axis, from -2 to 8, and on my y-axis from -50 to +350, and then a y-scale of 50. So again, that gives me this really nice looking graph. Now, the problem itself told us to skip by 0.5s. So what I can do is hit second table set, or second window, to bring us to table set. And you can see, oh, where do you want to start the table? And then the change in table, which is the next row, I've set to 0.5. Yours will likely be set to 1. So now when I go second and I go to table, it's actually going to load up the table starting at 0 and going down by 0.5 each time, and it gives me the y value. So I don't have to plug in the function each time. I can just keep scrolling to get all the way to 6. So that's super helpful here. It gives you a lot of polynomial evaluation. Essentially plugging in an x value, it gives you a bunch of them right away. So that's super helpful. So that essentially answers part A of our problem, figuring out the change in each of our y values. Now going back to the graph, we were asked to find the domain, the range, and the maximum. Thinking about the actual problem itself, the curve in here is what actually represents what the drug is doing in your system, because by the time it comes back to 0 down here, you won't have anything left in your system. So the domain is really going to be from 0 up until this value in here, wherever we stop. So we want to calculate that. Let's say second calc. We go down to 0. And let's see if we can't figure out exactly where that 0 is. I'm going to scroll to the right very slowly and try to get us a little bit closer to where we're at. I'll just hit enter somewhere around here, and then we got to keep going. And I will keep on clicking over until we get, since it's such a strange scale, it's just going by a really small amount each time, until we get to where I'm confident we've touched this 0 in here. Somewhere in there, it looks like. See how my y value is negative there? That means I know I've actually crossed the axis to go negative, and that's what I was looking for. So I'm going to hit enter right there. Again, notice my y value is negative. I know I'm actually to the right of where I crossed the axis. Hit enter one more time. And there we have it. The 0 falls exactly at x equals 6. So my domain is going to go everywhere from 0 to 6 for this application, because beyond 6, I can't have a negative amount of ibuprofen in my system. So we just cut it off at 6. Now I'm going to clear that. And then the other thing I want to calculate is that maximum value. So let's go down. I hit second calculate, and we'll go down to the maximum. And to find the left bound, I got to scroll all the way to the left, which will take me just a moment. Again, because of the scale of this graph. Okay, I'm now to the left of my hill. So I'm going to hit enter for the left bound. I'm going to scroll to the right of the hill. And I'm going to hit enter on the right bound. Hit enter one more time, and it will highlight exactly what that maximum was. So that goes, the maximum is 345.76, and it's at 2.148. So those are all the details we need to pick up from the calculator. Now we can jump back to our lecture. So remember, off the table, we can pick up this part A. I think my pen's on. Maybe not. Here we go. We can pick up part A right from the calculator. In the domain, we found 0 to 6 was the domain. 0 and 6 are included. And then the relative maximum was something like 2.14, and it was 345, around there. as a point, and so the max is 345, and it was at x equals 2.14, wherever that was. And then the range, of course, is from 0 to 345 included. Those were all our y values. So right off the graph, right from the calculator, we're able to get all of this information. Now we have just one more example. Here we're looking at a stone thrown downward with an initial velocity of 29.4, and the distance it travels is given by this function here. So if the stone is thrown downward from a height of 352.8, how long will it take the stone to hit the ground? Basically, we're thinking about how long until the stone has traveled 352.8 meters. Note that that's a distance, so we want to know how long it takes to go that distance. Essentially, we're setting our output equal to 352 and solving for t, our input. Well, of course, we want to use our calculator here, so let's jump back. And in this calculator, you'll see I have our function entered. I also entered our goal, essentially what output we're looking for, as a single number, almost as a separate function. Because then when I go to the graph, I can actually just check for where those two intersect, and it tells me exactly where, what t value, what time it takes to cross that line. That tells me what time it took to go that distance. So just to, if you're following along, here's what my window looks like. I'm going from -10 to 10 on my x-axis, -50 to 400 on my y-axis. So I really did have to fit this on my screen. That's what makes my graph look like this. Now, if I want to calculate where that intersection point is happening, I go to second, calculate, and I go down to intersect. And you'll see, based off where this point is, I'm clearly on my first curve, my blue curve. And then here, after I hit enter, I'm clearly on my second curve, my red line. And so I hit enter one more time, and it brings me to exactly where that intersection occurs, which is x equals 6, y equals 352.8. So essentially it took 6 seconds, I think it was, on our time units, for us to go 352.8 meters. Or no, was it feet? I think it was feet. Let's go back to the slides and find out. We'll get just the right units there. So, make sure my pen is still on. There we are. We saw after 6 seconds, we reached 352.8 meters. So 6 seconds is how long it took the stone to hit the ground. That's exactly what we're looking for here. So that is it for today. As always, please reach out to me if you have any questions.